check this is working. All right. So we're into this. Welcome back to the ChatGPT lectures. Good to see so many people here today and new faces as well. I like that. This is frozen. All right, I'm Harry Berg. Welcome back. This is really, I'd phrase it as a bonus lecture, and I think it is quite different from what we've been doing so far, but it stacks nicely on the end of programming for deep learning, and it's going to be followed by the intro to NLP starting tomorrow, and then the real core ChatGPT stuff next week. But today, what I want to focus on is custom datasets, pre-trained models, and fine-tuning. 3 key things that will really help you take this away from the toy data sets and bring it to the data that you might have collected from experiments or found online, and use some really powerful models pre-trained potentially by huge companies straight off the shelf, and then even fine-tune them specifically to your problem. So this is really practical lecture, and hopefully just a ton of time to code today. That's it. That's all I've got there. So what we're going to go through today, you can find all of these notebooks and the practicals in the AiCore portal. If you don't have access to that, just make sure you're on Discord and message Ahmad Al-Alti over there. But I want to start off with something where I'll just demo it to start with. And it should be a bit of a maybe recap, refresher for anybody who's getting straight into things. And it'll introduce nicely how we can create custom data sets, the rules they need to follow, and then how they would be used in a typical machine learning training loop. So firstly, let's just fire off from a few different people. What's happening in here? Somebody tell me what one line is doing. Somebody hit the next one. Over here, can you guys tell me one thing that's happening in this loop? Anybody feeling brave in the shirt? You look like you know what you're doing.
So you are affecting the optimizer?
Absolutely, yeah, that's one thing that's happening there. Cool. To start with, we need an optimizer. At the back, my friend in blue, anything else happening in this? What's happening in the next line? We go through the data set a bunch of times. That's what that line's doing, yep. And maybe you can do the next one as well. What's this? Yeah, batches of data in the data set. We're going to go through them bit by bit. This one I'll do, that's easy. The batch consists of 2 things, features and labels. I just unpack them into different variables. Down here, this one kind of speaks for itself. I'm making predictions. Over here, what's this line doing? Somebody from the front right. Wayne?
Calculating the loss, so the difference between the prediction.
Exactly, yep, exactly. And what loss function is that using? Why is that? What can you tell about this problem if I'm using the mean squared error? Classification or regression? It's a regression problem. Exactly. Great stuff. Cool. Lost or backward, harder one. Somebody in the middle. I know this crew here. You guys know what's going on.
Calculate the gradient of every variable of loss with respect to every variable preceding the loss.
Exactly. Yeah. So it populates each parameter of the model's gradient, and then that is using the next line. Maybe your neighbor can help out. What's this line doing? Yeah, so depending on which optimizer it is, but yeah, in the case of stochastic gradient descent, that's what it does. It updates the parameters based on the gradient, regardless of what optimizer. And then finally, maybe the toughest one, but we've talked about it so many times, it should be obvious. Right now, anybody in the back 4 rows over there? Feeling brave? Optimizer.0 grad? You know what's going on?
sets the gradient back.
Exactly, yeah. It sets them to none. But yeah, it resets the gradient so that there's no stale gradients there, because when you do lost dot backward, it doesn't get replaced, it just gets accumulated. So that's the typical training loop. Basically, the learning in machine learning is going through this process and updating the parameters.
Sorry, one question.
Yes.
Could you remind us what the data loader is exactly necessary for?
Yeah, exactly. Data loader does two things. Anybody help a friend out? Two things. What are they? It does the batching, so it batches examples together into small chunks. You don't want to
Why
pass.
are we doing that?
Yeah, so you don't want to pass in the whole data set at once, because every time, well, you don't want to pass in the whole data set to this line, because this line is just going to be used to make the updates for one optimization step. So if you're going to make predictions for every example in your data set, that might be a lot of processing just to make one small step. So the hope is that with a smaller batch, you get a representative enough sample of how the model parameters should be updated, and you don't need to pass in the whole data set, which is, it may not fit in your memory. It might take a long time to make all those predictions depending on what model you're using. Make sense?
Yeah, like one thing I'm just wondering, like, is how the batch size is kind of related to the number of nodes. Because I would imagine if like the batch size, like if the number of elements in the batch is like very small, and you have a lot of nodes, like I would almost feel like it wouldn't give so much information. That's just a naive,
Yeah. So I one thing I should point out, thanks for that. On this line here is that the model processes every item in the batch in parallel. So the batch size is independent of the model architecture. Yeah, it's independent of the model architecture, and so as a result, you can choose whatever batch size for the same fixed architecture. Make sense?
Yeah.
Cool. Good stuff. Great. Questions about this? This is key to understand, Wayne.
Where do we get the division between like batches and training sets and validation sets?
Yeah, so that is one thing that we would need to have done in advance. So probably we wouldn't have just data loader. We'd probably have like train loader, test loader, validation loader. And each of them would have taken some split of the data, validation set, training set, test set, and then you'd have batched each of those together.
Yeah, so you said that the data loader does two things. One was batching.
Two things,
the
one's
other
batching.
was the loading of data. Is that what it is?
Not quite. So that would probably be done in the data set. When you create an instance of the data set, that's probably when you'll load it in, store it in memory. Remember the other thing? It's not loading in.
When we like separated the features from the labels, or?
No, we'll do that here. Why did the loss? Remember that strange loss curve we looked at with the repeating pattern?
Oh, that's because it would like finish the epoch.
Yep.
Finish the batch.
Yes, but why does it always look the same every epoch? This is more detail than we need here, but it shuffles the data set. Exactly, yeah. So data loader does two things. Makes small groups of data, which should be representative of the whole data set, and it shuffles them every time that we go through it. Cool. So understanding that is solid. Ahmed.
You run the validation data loader after the training.
Maybe. Why? Why would you do that?
I'm asking, like, in the for loop, would you put it after the for loop for training?
Yeah, so you might want to, for example, in every epoch, at the end of every epoch, calculate how well am I doing on unseen data on the validation set. So you might, yeah, you're right there. You might do a full batch in validation set and use that just to compute the performance on that validation set there. Cool, great. So I'm not even going to bother with validation test splits so far, bad practice, but just to focus in on the point, if we go up to this cell, you can see that I've got a data set and a data loader, which are the key topics to zoom in on right now. But these ones, these ones are just off the shelf. I've got them from PyTorch. So in the PyTorch docs, if you just search PyTorch datasets, you'll be able to find all of the datasets which are available in PyTorch. There is a ton of different datasets, some you might have heard of, like SciFar or MNIST or ImageNet, all those kind of things. There's a ton of popular datasets there. And a lot of them have this nice built-in functionality into PyTorch, which makes it super easy, like trivial to get them, right? So this is kind of us playing around with toy data. Maybe some of the data sets are in there can be certainly used for some serious stuff, but you're not going to find every data set you want in this format, in this nice format, torch.give me the perfect data set for my very specific problem. So we want to know, how do you create something which behaves the same as this data set which you've loaded in straight from Torch? Because you guys have probably got raw files, right? I imagine some of us in the room have got, just like a big folder full of thousands of, I don't know, X-rays or something like that, or like the structure of different molecules. And all of that stuff, you want to be able to turn that into data set, which you can use in the same way. You can firstly pass through the data loader, and then you can plug it straight into this typical training loop, which looks the same in most cases. All that's really going to change is the data set and the model in most cases. Cool. So I want to run through a example of building a custom data set from scratch, just with some fake data. I'll just initialize random torch tensors. And then we'll go on to the practicals where you can do it from a file and then do it with more complex data type images. And then we'll move on. So the way that you got to do this is I want to create a class, which is my data set. I'm going to call it fake data set. And importantly, it needs to inherit from torch.utils.data.dataset. That is going to give it some useful properties later. And before I implement any of that in there, I'll just leave it empty for now. I want to show you how I'll use it at the end of the day, okay? Much like I've used this MNIST dataset, I've just initialized it maybe with some parameters, and I can play around with it like this. For example, I could do dataset, okay, give me the 10th item in that dataset, or I could ask, what's the length of the dataset? Those are the two key behaviors that we need to define so that PyTorch knows how to use it when it comes to putting it into the data loader, okay? And if we can put it into the data loader, then behind the scenes, PyTorch will figure out how to batch it all together and shuffle it and such. So as long as we define these behaviors, then the data set is fine. How can I define for my new data set down here, if I were to create an instance of it like this, how do I define how it behaves when I ask it for the length and how it behaves when I index it, ask for a certain item? Currently, this class, it doesn't have any behavior. It doesn't even have any methods it can call, it doesn't have any attributes. Does anybody know how you can define those behaviors?
Do you define methods?
Yeah, we're going to have to define some method. So you can imagine it's something along the lines of like getLen, right? There's some function which is gonna be able to get the length, and it's gonna return, let's just put a fake number there for now, it's gonna return something like that. But that wouldn't let me do this. That would mean I have to do dataset.getLen. And that's a bit unintuitive. I want to be able to use Python's built-in functions like the len because it just makes sense. The length of a dataset should clearly return how many examples are in the dataset. So I'll give a clue, or unless Wayne, you got it?
Oh, can you override functions?
You can override functions and methods to get the behavior you want, but this empty class won't have these behaviors defined yet. I heard it from somewhere. Yeah, someone got it. And you put your hand up. Do you want to?
Maybe extend some existing data structure to pick it up.
So again, this thing hasn't got any methods implemented, so we don't want to really extend it. It doesn't really have much to extend so far. We really need to implement it from the ground up. But we will store our data set in like some native Python data structures. Yeah, we'll probably have like a list of examples or a tensor. But someone over here.
Underscore len underscore.
Very close.
Magic method.
Magic method is the correct answer. Yes. My friend there, I should really get your name because we've talked a lot. But you said underscore len underscore. Very close. Very, very close. Underscore len underscore. Why? Why do I have to call this method which implements the behavior for getting the length? Why do I have to call it double underscore either side? What does that mean? Double underscore either side.
You're inheriting it from the
Not inheriting it here, no.
It's one of the magic methods without like you pull it using the lens.
Exactly, yeah. So this is a magic method. That's what the double underscore either side means. A magic method, what is that? If you're not aware, it is as simple as this. There's one sentence you need to remember. That is, magic methods define the behavior for a particular syntax. Different magic methods define the behavior for different syntax. This one, double underscore len double underscore, defines a behavior for calling Python's built-in len function on the dataset. You may be aware of the first magic method you should learn about, which is init. Now you can look at that through a different lens, right? What does it do? It defines the behavior for a particular syntax. And in our case, this is the syntax which it defines a behavior for. Round brackets after the class name. And there is one more magic method which we need to define, and that is the one which defines a behavior for indexing. Anybody know what that is? What was that? Get item, exactly. Thank you, sir. Get item. So those are the three methods, all of them magic methods, and the only methods that you need to implement to define a PyTorch dataset. These three things allow you to, in any way that you want, define what should happen when you create this dataset, probably load some data in and store it as an attribute. What should happen when you index the dataset, probably return you a pair of features and labels, and what returns and what's the behavior when I ask for the length of the dataset. Probably like just count how many examples there are, right? So I just want to really highlight this right here. Whatever your data, whatever format it may be, whether it be images, whether it be some kind of crazy data that I've never seen before, whether it just be straight from a CSV, whether it be made up on the spot, you can follow this formula, and this will let you build a data set that allows you to pass it into a data loader so that you can use it for all of the deep learning models that we're going to see going forward. So, fake data set, I'm just going to do something like self.features is equal to, if I import torch. So I'm just going to have a torch dot, maybe we'll have torch.rand, and it's going to have a shape 100 examples, each with 4 features, like that. And I'll say self.labels is equal to torch.rand with 100 different data points there. So this would just be like, again, just made up data. I'm just trying to prove a point here where now any instance of this class is going to have those 2 different attributes, features and labels. Now I'm going to define how I would index a particular item out. What would be returned when someone asked me for, like I have done down here, example number 10? Can anybody help me out? What would go in this line? What goes here? What are the features equal to? So this get item, what I want out of this is just like a single example, probably a pair of the features and labels, okay? So what are the features? Not a trick question, this one should be easy. I've got all of them in the list, I just want one instance. Self.features, but I only want one of them.
Index.
Yeah, at a particular index. So let's do that here. We do self.features at a particular index, and self.labels at a particular index. And this getItem method, whenever you put square brackets after something in Python, it needs some index to be passed in. And when you do that, it gets passed into here, like that. So that's the getItem method, right? And again, whatever your data format is, just return like a pair of features and labels. If you have a supervised data set, that is, one which has both features and labels. And what about the len? Who can help me with the len function? How long is this data set? What number should be returned from this len method? What should be returned from calling Python's built-in len on the data set?
So we've got 100 examples, so we want to know that number 100, right?
Exactly. Yeah.
So we just kind of want to like not like enumerate, but might be like how many examples are there in several pictures.
Yeah.
So like yeah, there is like an inbuilt function which is like length of.
Yeah.
Like
Len of.
Self of features, and
Yeah.
we want the first dimension. No, because
You actually don't need it.
Yeah.
Yeah.
Exactly.
So the len of a torch torch sensor will just be the length of the first dimension.
Yeah.
So again, I missed myself there to decide which instance of the class. That's a data set. That's a whole data set there. And if I run this now, as long as we haven't made any mistakes, it should initialize. The length is 100. And if I print an example, you will see that it gives you this tuple, a pair of the features, these 4 numbers, and the label, in this case, just a scalar. But again, that all came from us choosing and being opinionated about the particular data we have and what should actually be in here. So whatever your data set, you can change those around. You can write the code that returns an image. You can write the code that returns like some text broken up into different numbers. We'll do that later. But this is how you create data sets in PyTorch. So with that, and I'll leave this example up on the screen, go to the AiCore portal, find the notebook on datasets. It's called Custom PyTorch Datasets number 6. Check out the practicals and open up this making a PyTorch dataset example. Hit create notebook, and we'll spend 15 minutes doing that. But basically, it's implement this house price dataset. Follow the formula, which I've shown you here. Let's have a go at that now. Not this straightforward, but you can still do it. So remember that the linear models they have more than one. And that's basically it's what more than one. So you'll get more than one star. Anything about the
Yes, the object is the same. I want some objects which have some parameters as well. So they can have they might also have them, depends on and then you go to the same month, so you can go specific objects in the picture, and then I want to select a picture returning number 10. That picture returning number 3. So I have this one, it's if I leave it once, it's like this one. Yeah.
So it's so that for the simple that's how you could you just return instead of yourself labels being and then you can regress all those
So
it's probably very simple.
I want it to be like put it like a different constraint. How about I take this thing?
I think like there's a bunch of
Yeah, that's the and then that Yeah, and that would be that format that would be massively
Well, you probably need to adjust that because you can imagine it's like you want to do that. So you want to get something. And then they'll probably get it to the then you can read it. And this is where you work in the loading the system
so
I'm sorry.
it's like boring and not
Yeah, I mean, and we can take a look later this lecture at some of the pre-trained models.
Yeah.
Just do that approximately, and they'll probably show us.
yeah, this is the this is the important part of the implementation. Yeah. It's like microscopic process. I know it's done, it's like an interesting idea, but I'm not sure. Yeah. How it's done. So I think it's very hard. It's like, yeah, it's like really disgusting. So, yeah, so, so I can just read my. Wait, if you have this, like later then you can kind of and then you return no, they're not I tried to read some of that, just not like get me relaxed. The remarks we can't about work piece and it's because they have to go and write it. I just have to do I have actually considered this. I think I remember. Work? No, indeed, I'm surprised. It's not a good item. Or sometimes they can send the chef. And then he goes there. And so the way they work, images which we share, image, and not change. How that works. I was unable to address it. And therefore, Yeah, but it's not. It's just not true. It's just not true. You can imagine anyway you want it. But this is not.
I'll do this now.
But I was trying. Like I would say.
Okay, so one thing is giving a little bit of trouble here, which I'll highlight. And if I get this started, just run that cell. What that does inside there is it downloads a particular file. So you've got this file with that name there. Define the libraries I'm going to use, and then down here, this tells you to use the gen from text method to load in that data. So if I say data equals gen from text and try to ask for this bostonhousing.csv and then print that, again, just print as much as you can so you can see things like that. I'll need to make an instance of that. Like that. If I run that, I get this. That's not what I want. Anybody found a solution to that yet? Or why that happens?
Can you show me for that?
Yep. I've just done gen from text Boston Housing CSV.
I used the
Mm-hmm.
I put it to comma just to try.
Yep, probably. So gen from text, it looks like it's not expecting. It's not by default assuming that different columns are separated by commas. And one thing that I thought was suspicious about this is if you print the length of it, I bet there's as many nans as there are rows in your CSV. So what it's done is basically said, okay, I'm just going to assume each row is a different item. I'm going to try and cast each row into a numerical value, but they've got all kind of text or different spaces between commas in. It doesn't make sense. It's not a number, which is why you get this full of nans. So if I was facing this issue, here's how I'd solve it. We just did this over there. It was good work from my man. I do Python gen from text nan. Okay. Search that up. It says gen from text returning nan rows. This is how you tackle that. So here's the issue. As quick as you can, just validate this is the same issue. Yes, looks like somebody's getting the same problem as us. Scroll down to the first answer. This one says, okay, you want strings, try data type equals none. So this guy's saying, all right, try the data type, but he's also got a few other parameters which I haven't got, including this delimiter. And that's the first one he's got there. So I would make sure to include that. And then if we go back to what we were working on here, put in that delimiter, run it again. Now we get something more reasonable. Still an issue with this. What's the issue with this? Header. How do I fix the header issue? No. Names, not named is true. Let's look at the docs. Gen from text. You could also use pandas, which is probably a better solution here, but scanning the call sign here, you can just see, right, is there anything useful? Well, this one looks suspicious. Skip header. Skip header equals 0. What does that do? What's that number? Let's go to the more specific detail. Skip header int, it says the number of lines to skip at the beginning of the file. Fantastic. That's what I'm looking for. Just skip the first one, please. Skip header equals 1. Run that. Data looks good. So that's the data you want. All right, I'll leave you go from there.
It's like it's basically like a powerful tool. Yeah. I did. I just like at the moment it's 70% like it just says I did yeah. No, it's different when it gets enough. It's
You are wondering why they why it's because or you can transform the strings
All right. Looks like everybody's getting through that pretty good. I'll share the answers for this later. Really, it's very much the same as the one we just did. As soon as you load that in, get the matrix in the right format, it's just a case of slicing off the last column and saving that as labels, and keeping the rest and saving those as the features. And then beyond that, again, just take the length of the data set and then return that pair of features at a particular row and the corresponding labels. Any questions, or people want to dive into this example specifically, or should we move on? What's that one?
Why is the last one?
Just the way the data is stored in NumPy matrix format. That's why the last column is the labels. Yeah. Cool. So I'll share the examples for that later, and maybe we can spend 10 minutes now doing a little bit more of a complicated example, which might be more relevant to some of the stuff that you guys are tackling. So this one is around images, okay? And I want to try and run through this quickly to just highlight how this would work on a different modality of data. So in here, we've got an images directory, which is full of folders, and each of them corresponds to a different type of animal, and those are different classes of your classifier. By the way, if you happen to have a multi-class image classification dataset, this code will work exactly for your problem. Just change the data that's in those folders, okay? So one big folder full of images, it's got subfolders called different animals. Those are the different classes. If you wanted to classify different types of, I don't know, buildings or whatever, you would just change the folders to be named the different types of buildings and include corresponding images inside those folders. So I'll run through this and kind of show how we could implement a image dataset. So importing a few things here, including the dataset and the data loader, and also this one from Python image library, import image. And finally, this transforms. So one thing that we're going to need to do in this dataset is transform the data in more complicated of a way rather than just turning it to a torch tensor. It's going to be an image when it loads in, and we need to somehow convert that to a torch tensor. So torch vision, PyTorch's vision library, computer vision library, contains a bunch of utilities for working with computer vision. So run that. And here, I've got to write a function to get the list of class names, okay? So what I'll do for this, again, I'll just, this stuff you could find just by searching it up, but I'm going to import the OS library. OS is basically gives you access to the operating system to do things like os.list what's in the directory that you specify. So I'll list what's inside the images directory. And I think it should be as simple as that. Return class names. In fact, I could have just done return that. So return os.list images. Let's see if that works. No, it's not been found. Click on this folder, you can see what's here. Right, it's got a lowercase, so need to lowercase that, run that cell. There's my different classes, okay? Don't want to do this one. That's just some extra data store. So I'd say, let's just filter that out. Can I just delete that? That's really annoying. I'll just do a quick list comprehension. Don't worry too much about this, but it's a very simple way to filter a list. basically C for C in class names if C not equal to dot ds underscore store. Run that. There's my class names. So here is my different classes. They're going to be, as me and my friend in the pink were talking about, the different labels which you need to know, but you're probably not going to, well, you're going to need to convert these into numerical values when you use them in your model. Brilliant. So now we've got the class names. We need to create a class called animal, which will collect all images from a class. So in here, what I'm going to do is I'm going to get a list of all the file paths and the images inside the subfolder and assign them to the attribute self.images. They should be of the format like this, okay? So again, I could use OS here. I could do os.list dir, this time inside, not just inside the images folder, but inside the animal name folder. So what I will do here is I'm going to format a string by putting an F in front of it, start it off with images, and then follow that by the animal name like that. So that should list everything that's inside that particular animal folder. Image names is equal to that. And now I need to add the file path in the front of that. Before I do that, let me just print the image names so you can see what that looks like. You can see I've got this image followed by a number.png. So now basically for each of those images, I just want to prepend this on the front, or in fact, all of this. So I'm going to take that, I'm going to say image file paths is equal to, it's going to be, again, right, I'm going to take this list that I've got so far, this image names. So image name for image name in image names, that will just give you the same list. It's like a one-line for loop. But instead, the thing I actually want to return is not just image name, it's this thing formatted with the image name here. So what I'm saying here, could have written this in a for loop, but I did it in a nice one-line list comprehension. Basically done a for loop for image name in each of those image names, but then I've replaced it with this value. So let's take a look at what that looks like. Again, if that's trouble for you, you're not too familiar with Python, then just do it in a for loop in 3 lines instead of 1. But now I've got this. So now I've got all of my different images. And somehow I want to turn them into, I want to read them in from those image file paths. Well, that's what I imported image from pill from. So you can do image, is it image.open? Image.open, it takes in a file path. So if I give this a file path, such as image file paths 0, then it's going to give me an image. And if I print that image, it's going to give me this pill image. This thing looks horrific, but that's just telling you it's a pill image data type in Python. This thing, it has useful methods like .show. So if I do image.show, doesn't show up in Colab, does it? I have to call the built-in display function.
Oh, so annoying.
Yeah, well, if you're in a Python script, that would show the image. If somebody can look that up, that'll be useful. But the basic point here is that I'm trying to get to a place where I've got all my images as in that pill format. So I don't just want to do this for one image. I want to do this for each of the images. So again, in a list comprehension, or maybe I'll do it in a for loop now just to make it simple. So for image file path in image file paths, I want to image.open that image file path. And at the top of here, I'd have images as an empty list, and then I'd do images.append the image like that. So everything that's happening in these 4 lines here, above, I've done that in 1 line. Those simple list comprehensions. Can everybody see that? Does anybody have any questions about the list comprehension and how that works? How that's similar to doing things in a for loop?
Can you have these saved and shown to us?
Yeah, I'll send the solutions out later. But basically, I'm saying I want a list of images, and for each of those image file paths, go through and use image to open that image file path. It will give you a pill image, which is this thing printed down here. That thing, you can see it's a RGB image. It's size 296 by 169. And then I want to add that to my list of images. So in this animal class, I've got all those list of images. And I'll probably set self.images equal to images, like that. Self.name equals animal name. And then this show, it says it should display a random example from the list of images. So I could do import random. And inside this method down here, I could do random.choice self.images. That gives me an image, and then I just do image.show like that. And that should show a random image. So this is just like a utility. This is just a useful kind of tool that you might build when trying to create this data set, right? This thing isn't necessary to the data set, but you can kind of see that depending on how your data is formatted, maybe it's in these nested folders, maybe it's in a database, maybe it's, I don't know, in some weird format where you need to combine different files or something like that to get it. Then you might need to write more code around just the raw files to get it in the format that you want. But now I've created this class, this animal class, I can use that to get all of my pill images just as I want. So I could do my frog.images or .images as it is there. And that would give me a list of these different pill images. Oh no, the DS store has come back to haunt us. Why has that happened?
I think when you define image FBS, you need to not take in the OS.
Yeah, is that in this
Yes.
folder, do you think? Okay. All right, there we go. So there's a list of all of my Python image library images. These are literally like the image files, the PNG files you've got put in a folder somewhere, saved in Python. Now Python can use them. And this is actually a really flexible format that you can do all kind of things with. You can do more than just show, you can do image.convert to grayscale, you can do image.crop, image.rotate. So however you want to transform this data as well, which might be necessary down the line, then you can do that easily from pill. So we've done that. Moving swiftly on to not take up too much time here. Here's how you can make a transform, which might be useful. You can use this transforms.compose things to create a bunch of transforms which will be applied one by one. And so in this case, I need to add a transform to resize the image, add one to convert the image to a PyTorch tensor. These all come from PyTorch. So you can search torch transforms. And let's have a look at that. No, let's look at the actual docs. So transforming and augmenting images, it says. I'm going to go down to Torch Vision docs. And in here it says, okay, yeah, so this is where we were. So there's lots of different transforms that you can apply. So you can see like center crop, grayscale, pad, random crop, resize. All these things can be used in Torch. Zoom in for you. So what do we need to do in our example? I need to, where's it gone? I need to resize. So I'm going to open up this resize. And you can see how this works. This one's a class, which you must initialize with the size which you want to resize to. And then it has its own forward method, actually, interestingly. Like we've seen the other layers in Torch have, this transform also has a forward method. But the way this works in practice, just to cut to the chase, is that you would do something like transforms dot resize and pass in a shape there. Maybe I'll do just 100 by 100. That thing there is a instance of a class which can be called on a pill image. And everything inside this transforms.compose is also an instance of a class which can be called on a pill image, and it will apply that transformation. But note, the resize is a class. So this thing has to be initialized first, like this. You're initializing the transform by telling it what size it should transform thing to, before it's actually called on the data. So just as an example, let me go back up to my image files up here. So I've got my frog.images. I'm going to get the 0th example, and I'll print that. So then we should just see a pill image. Then I'm going to apply, then I'm going to create this transform. I'll call it T, like that. And I'll call my transform T on my image. And then we'll print that. Okay. So let's see what comes out here. I get an issue there. Key error 100. What's happening? Okay. What's happening here? It says there's an issue when I've tried to pass in these two numbers to my resize. Very common issue. Look at the docs. You can see that the first parameter, and only the first parameter, is size. Not the second one. The way I wrote it, I gave it two parameters. Firstly 100, second one 100. So those things, they both need to be in brackets as the first parameter, like that. Run that. Oh, there you go, now it shows up. So you can see that I have gotten this image, printed it as an image, which looks like this, and then done a transforms.resize by calling that transform on my image. I'll pause there, take a drink. Any questions, or wanna challenge me to play around with that, or try something else out? Let me know, and we can do it. Hopefully that's somewhat of a clear example of how the transforms work. You got to initialize them based on what transform they're applying, and then you can call that transform on the data. And if you have many transforms, you can put them inside transforms.compose. This thing is then can be called on the data. Question?
You want to filter the images with lower resolution, how can we do that?
If you want to filter the images with a low resolution, how could you do that? So I'd probably have like a pre-processing function, which you just run once, and then it filters out the dirty images into a different folder or something like that, rather than put it in your data set. Because if you put it in your data set, every time you use that data set, it's going to do the same boilerplate operation of removing them. But to do that, you could do something like load them in pill, and then look at the size. So I think you can do like there's an attribute of these pill images. What is it? Is it dot size, like that? Yeah, if I run that, it gives you this size. And so that's a tuple, and you can simply say, if this is less than 100, remove it from the data set. Yeah. So I'll share the solutions to this later, and hopefully that'll give you a chance to play around with these transforms. But how would that actually look in the data set? Well, in the data set, you could, or what you'll often see is that the data set's take in a keyword argument transform. And in the initializer of the data set, you'll say self.transform is equal to transform, something like this. And then when you get the item, you'll probably apply that transform. In this case, I think that that we're maybe applying the transform in here. Oh no. Yeah, okay, well, forget that. So let's just say I assign this class's transform attribute inside the initializer, like that. And when I do the get item, I would do something like this. So I'd say, image is equal to, what have I got? I've got self.all-images. Self.all-images at a particular index. And then I'd say something like this. I'd get my transform, self.transform, and I'd call that on the image like that. So when you're indexing this data set, you're getting the items and then transforming them and then returning them out. So you'll probably find that the data that you're dealing with needs to be transformed. If it comes in any format which isn't already numerical, it will need to be transformed somehow. And you can use those transforms built in by PyTorch, or you can create your own depending on what you need. Cool. I'll give 5 minutes to play around with that, and then we'll get moving on with the custom models, which will be very quick and easy, and then we'll look at fine tuning. All right.
So there's some point of
So like the lots of work in that, like I will only work like once or twice a week. Yeah, exactly. So anyway, so I'm not going to this is more like there are so basically, no. So this one, MATLAB exercises from like MATLAB commands over and the overwriter will give me numbers and see if it's so that and then the next is and this is the like you can do it forever. And it's good. But then then this one so this one you submit it in, but it also has
All right, so let's move on now, guys. That was a whirlwind tour of how to create custom data sets and just skimming over the top essential parts to understand. There's loads more to this. So if you are interested in doing more of it, let me know and we can probably help with that. But those notebooks should give you an idea of how you can begin to get something set up at least. There's two more things I want to go through today. We only got 40 minutes left, so I'm going to jump into it. The next is this notebook on pre-trained models. So if you want to pull that up, this notebook, it should be pretty simple. And what it highlights is how you can incredibly take the hard work of incredible engineers and big companies that's been put in to train very powerful models, and you can take them straight off the shelf. You can download them and use them immediately. So if you want to tackle a problem which somebody else has tackled before, then, or use that as a starting point, then you can get that hard work straight off the shelf. And one of the best places you can do that is on Hugging Face. So if you open up Hugging Face, Hugging Face is a website which has basically become the largest repository of machine learning models and data sets on the web. You can access pretty much every large model which is publicly available on Hugging Face and all of the data sets with a really easy interface. So one of my top recommendations would be get comfortable with using Hugging Face. So looking at the list of models here, you probably recognize a few of these if you're anywhat familiar with the landscape of deep learning. You can see BERT, you can see GPT-2, you can see T5, Roberta. They're a bit more niche, but at least GPT-2 and BERT you've probably heard of. You've probably heard of GPT-3, it's not on here, but GPT-2 is. GPT-J also is, which is much bigger than GPT-2. So on here, you can access any of these kind of models. And I think what I'd like to do is to give you a chance to spend some time playing around with these. But to run through how you do that, you simply click on the model. You can read all about it. You can look at the model card, see what it's used for and what it should and shouldn't be used for. You can click somewhere over here to use in transformers, use in the transformers library, which originally was developed by Hugging Face and was the place to get transformer models, which you might have heard of, like GPT. But now it has all kind of models on, not just transformers. And in here, you can get a code snippet, which is exactly how you use this thing off the shelf. So for whatever problem that you want, a good starting point can be grabbing this stuff straight out of Hugging Face. So here you can see it's really easy. You just take from transformers, import auto model for masked language model, and then you can do from pre-trained but base uncased. And this will give you the model, which works in exactly the same way as we've seen in the lectures so far. You can get that model and you could use it in the same kind of training loops. You could use it to make the same kind of predictions straight off the shelf. So to come back to these list of models, there is so much stuff that you can use them for. You can see on the left-hand side, you've got different sections. For computer vision, Dahlia, we talked about object detection earlier. You can click there, you can see state-of-the-art models on object detection from Google, Facebook, Microsoft, etc. You can see down here text models for summarization, translation, all the way down to reinforcement learning and models for robotics. So this is an amazing resource.
Sorry, so Google actually uploaded it for free.
Yep. Lots of companies, amazingly, right? Amazingly, upload lots of their hard work in the form of model weights and parameters onto this website. And you can pull them straight off and use them.
Like not all though, because for example, like GPT-3, OpenAI,
Not all,
making
yeah.
money off of it.
Yeah.
ChatGPT, right?
Yeah, exactly.
Some of them.
Yeah, many, a lot of them are closed source, but all the open source ones, like this is the place to find them. And like, there's a really good starting point, right? So there's a lot there. So I won't actually go into this too much because I don't think we really have the time. But you can see, for example, this is how one example would work. You get an image, you can open that image with PIL, like we saw previously. You get the model from the pre-trained weights. And then you basically format the inputs and the outputs in the way that's expected. This is just copied from the clipboard in Hugging Face. And then you can process that model using some simple logic. So if we run this, should see it start to work. You'll need to install these other libraries first. So the transformers library is the one that contains the models.
Who's the client?
I think it doesn't print all the sub dependencies as it's installing them when it's got that --y on the end. So yeah, there's not too much of a specific formula for these. It's really like the input and output format varies per model. So the key thing, right, is not for me to be able to explain this this code to you here. You can probably read it yourself, but it's to understand how to get the code from the transformers library. So let's say we want to do object detection. We can go to this table transformer detection. Look at that in transformers, and I think in a lot of them you can see examples of how to use in different places. And from that, yeah, you can use them straight away. So is this working? Let's have a look. One thing that's worth mentioning here is that some of these models could be huge. Some of them can have hundreds of millions of parameters. So if you are downloading them on your laptop, just be careful to not fill it up, because I've hit like too much memory full that I can't even delete the model at some points. If you're on Colab, it should be fine, but you may not actually have the RAM or even disk space to download them anyway. For example, you might not be able to fit GPT-2 on your machine. So you can see it's taken a load of time to download. That's because this model is pretty huge. Okay, cool. So take 5 minutes to take a look at that and just understand what's happening there. See if you can run that. See if you can find any other interesting models on Hugging Face that might be useful for your work. But I won't spend time talking through the code for that specific model there.
This is new. Just press this on the side. It's also, it doesn't return. But it's still
Wayne.
This one, they should actually speak. They're still rushed, that's fine. Mine is from a specific base. Which gets. It might be in that same range. Maybe. Yeah, because there are models which are eligible. They go up like for 3 years. And basically, they see this. Which is basically the best in time of the challenge. So if you get the yes, it's 2015, 2019, some of them. So good for you. But you have to like more version on the machine. But yeah, I think so that's the one that I've got in mind. The last time, because I already had a presentation, I was going to break it all. I just but I was just looking out, and I'm trying to go through the glass without the because I think and then they just don't do it in 2 weeks, so I'm gonna have to come back for it. If I can make it 2 weeks, maybe we can get it. It is, exactly. But I don't think I'm sure it's fine. If it's a work, my story, and I actually sent one of the three that I have. The one one's from work, and then the third one, because my girlfriend gave me my girlfriend to so and then I never used it. So like I've got yeah, but I'm still used to this one, so yeah, not exactly 95, but yeah, this is fine.
Okay, so here's one here's one example that I just ran. Yeah, again, like I literally just copied that off Hugging Face. So I went to Hugging Face, I looked at object detection, I found this model, YOLO V5N V7. I copied this, of course, after I read it and understand what it does. At a high level, it loads in the model, it sets some configuration, it gets an image, it makes a prediction on the model. That does it with a different larger input size. It gets the predictions, and this results.show is what shows me this image, probably because the results is a pill image, like we looked at before, right? So you can see, here's my image. It's got these bounding boxes in the right place. I don't think that handbag is quite correct, right? But you can see it's a low confidence anyway, right? So you could have set the confidence threshold higher, and all of that is just done through these configurable parameters up here. So here's the confidence, only 25% there. I could change it to a 75. Run that again. Let's see what happens. And there you go. So now it's only predicted things which it has with certain confidence, okay? Not confident enough that's a person, apparently, with that expression. All right, so any questions about just using Hugging Face at a high level? Again, just want to go through that super quick. It should be pretty self-explanatory, and all the examples are there anyway. But that's how you could get started with using pre-trained models straight off the shelf. All right, so now I've got a new question, which is there something in between using an off-the-shelf pre-trained model and training from scratch?
Yeah.
Is there something in between there? The trade-off here is that if you use an off-the-shelf model, pre-trained model, then it's going to be less specialized to your problem, but you're going to get to results really quickly, like I just did in 2 minutes. You know, get the object detection model off the shelf. If I train from scratch, it's going to be very specific to my problem. That's great, but it's going to probably take me ages to figure out what's the right architecture for my model and train it, and it might be too long to train. It might be debugging required, all that kind of thing. But inside that spectrum, between those two things, is there something in between? Yes, there is. And that is fine-tuning a pre-trained model. So the obvious reason why you might want to do this is if you have a new data set for the same kind of problem. So let's say you have you've got a pre-trained model which is trained on ImageNet. ImageNet looks at all kind of objects in the wild, and you have a data set which is specific to Oxford University. So, you know, maybe there are subtle differences between things. So you want to train on that data set so it gets good in this domain rather than just being a generalist everywhere. So that's the first kind of obvious case where you might want to use a pre-trained model to specialize to a particular data set, but the same kind of data. Other cases are where you want to use that as a starting point and take a lot of the pre-trained weights, which should be useful for a different kind of problem, and apply them to your new problem. So you might have a bunch of different classes. Let's say you only want to classify between 3 different types of bicycles that you see riding around the city. Well, you might get a pre-trained model which contains a lot of the parameters which figure out the right things in the beginning of the model, and what's output from there would be useful for you to train a smaller network on after that. So you could take the outputs of a fine-tuned model and train on how to predict them for a different set of outputs. That's one thing that you can do. So when we do that, we're going to basically take a pre-trained model off the shelf and either update some of its parameters or add another layer to it and then train those last parameters. And the model that we take off the shelf, we call that the backbone. That's like the starting point for the model. So you might say a very typical backbone would be taking the ResNet 50 backbone off of Hugging Face. ResNet 50 is a 50-layer deep computer vision model trained to classify the ImageNet dataset. The ImageNet dataset is a 1,000-way classification. There's 1,000 different classes in it, and it produces a probability for each of them. Now, during the training, that model is going to learn lots of useful things about images. It's going to learn what kind of shapes are indicative of different classes. It's going to learn how to combine the raw pixels in a way that the network has activations for useful things down the line. So a lot of what ResNet will be, a lot of the parameters in ResNet will contain just generally useful image information, right? How do I process images? How do I detect things which are useful in all kinds of general image problems? And then you can stack on the end of that your final model, which will combine what's been learned so far into an output. So let's look at that. So this is a diagram of what I'm talking about. I'm talking about replacing the model head. That's what I want to do. So you get some neural network off the shelf, you take some input, and at the end of it, it's got this thing we call the head. The head combines all of the activations in the layer before to actually make the predictions. So these are the predictions here, and in the case of ResNet, you'd have a 1,000-dimensional output from the model head, produces a probability for each of those different 1,000 classes. Now, if I have a different problem where I've only got 3 classes, I want to replace this model head with the same kind of layer, linear layer, which just has 3 output shapes. And by doing that, then my network will be the right shape, but I'll still have all the same parameters from the earlier layers of the network. And by doing that, then you can either, well, if we add a new layer, you'll need to either train the whole network parameters, or you can just train the last layer. And there's different ways to do that we'll look at later. So that's the first step. The first step is replacing the model head. But there are 2 ways to do that, and one of them is a very common mistake, which I just want to highlight. And then we'll look at the correct way to do that. So this is the incorrect way to do it, right? Is you take a pre-trained model, which has this pre-trained head on, and then you add on top of that a new fine-tuning head. Can anybody explain the problem with that from this diagram? Well, the problem is,
So when
go on.
the pre-trained head would give you already like a kind of output, which is related to like whatever the data was like used to pre-train it.
Yeah.
So then it's like, it's as if you were trying to train a fine-tuned model only on like those available like outputs.
Yeah, exactly. So we're going to add this new layer, and if we don't replace the pre-trained head, then this stuff it represents like the classification of the data set that it was pre-trained on. Not necessarily the features which will be useful to our problem. If you think about having a network which is trained on all kinds of different objects, including cars, and I've got a new network which I want to train to be a specific car classification data set, then if I pass my 10 different types of cars into the pre-trained network, they're all going to come out as the same classification. This is a car. Okay, I think ResNet, it has one, or sorry, ImageNet has one class output, which is like a sports car or something like that. And so if I pass all of those inputs in, you're going to get the same values in this activation for all of them. So essentially all the useful information which differentiates them, which might be found at the earlier layers, things like, okay, how big are the wheels, or, the shape of the different parts of the car, all of those stuff has already been combined to say this is a car. And so in this layer of activations here, you get mostly zeros. Mostly zeros, and one has a really high probability. So you basically get this one hot vector passed into your fine-tuning head, which is what you're then asked to make the prediction from. And that's really hard. So you basically, you've collapsed all of the data into this one node here, which is very high. All the others are zero. And then you don't have much information to actually make your new classifications from using that fine-tuning head. So what's the correct way to do it? It's to replace the head like that. So if I expand this, you can kind of see there, two ways to apply the head. Don't do this way. You need to replace the head, not add to it. So you should throw away the old head and add a new one. Any questions about that? Okay. So the question is then, how do we train that? Anybody talk about like what do you think the training process would look like?
You might have required spread stuff for some of the previous, like the ones we do in the training.
You might what, sorry?
After the required spread, you might have that more.
That's exactly one of the approaches we'll do. So you said for the earlier layers, we might set requires grad equal to false. And so what that would do is it'll basically say, once I use this whole model from end to end to make a prediction, calculate the loss, and do dot backward on that loss, PyTorch isn't going to bother calculating the gradient for all of these potentially hundreds of millions of parameters. Instead, it'll only compute the gradient for the values in this layer, which there might be a lot less of. So it can be a lot faster to do that. And it also has the benefit of, you've got this model, you've got this pre-trained model, hopefully because you think it's going to be good. You think it's going to be useful at the problem that you want to tackle. So you probably don't want to change it too much. And so by setting requires grad equals false for these layers, then you retain all of that information. And so this backbone acts as a fixed feature extractor, you might call it. The values that appear in the final layer of the backbone, they are these high-level features that have been built layer by layer up to the point where they should contain useful information, which can be combined by a brand new head to make a classification directly. So instead of containing like the raw pixel values, as the example I always give, they contain some high-level information like, okay, how smooth was the car, how big were the wheels, this kind of thing. So hopefully that makes it easy to classify on the end. And you only have to train these final parameters. That's one way that you can go about it. So that is what we call...
One question.
Question over that.
If you want to train more than one layer, what good way do you think is to set how many of the left layers you would like to update?
Yeah, so you can absolutely add more than like one layer head on the end. You could have a deeper model on the end if you want. In terms of what should the architecture be of the layer which the modules which you stack on the end of that, I think the rule of thumb is keep it small. If it underfits, add more layers or add more width and play around with that. Yeah, all within reasonable time and compute that you have available.
Experiment.
Yeah, experiment, but keep it small and keep testing and see if you go along. Question?
If you want to train the final layer of the pre-model of performance
Mm-hmm.
new head that you added, yeah, maybe that.
Yeah, so question was, if you want to train, let's say you don't just want to train the last layer, but you want to train maybe the last one and the one before, maybe the one before that. Can you do that? Absolutely. You just set those requires grad attributes of the parameters in that layer equal to true, whilst the others would be false. That would be one way you could do that. Okay, so what we're talking about when we're talking about setting the requires grad parameters equal to true, that's really like very PyTorch specific language we're talking there, talking about this grad attribute. All we're really saying is like, don't update some of the parameters, right? So if you use a different framework, TensorFlow, Keras, it might be different. It might be different terminology. But in general, that's what we call weight freezing. So you've totally frozen these weights. They cannot change just because I'm not computing the gradient for them and the optimizer is not optimizing them. So that's one approach to fine tuning. And like I said, that has the benefits of it's very quick because you only have the new head that you've added parameters to train. And all of the knowledge is retained from the pre-trained model, which hopefully you picked because you think it's going to be pretty good. However, depends on your problem whether it might be too rigid or not. So you might want to maybe slightly update all of the parameters from the earlier, from the backbone as well. And a different way you can do that would be, you could either train the whole model from end to end with the same optimizer, basically requires grad equals true for everything, or you can say, well, I know the pre-trained model was pretty good, so I don't want that one to change too much, but my new layers, they can change as much as they want. And the way that you could differentiate those two things is you could have two different optimizers with different learning rates, so that the new layers have a large learning rate and they update quickly, and the earlier layers from the backbone, they have a small learning rate, so they stay quite close to what they were originally, but they can still flex a bit to specialize for your problem. And we call that discriminative or discriminated learning rates. So if you want to read the details, they're down here in this notebook for both of these examples. So let's have a look at what that looks like in code. Here's my weight freezing classifier. I've got a class. This one just inherits from a classifier actually, which I've got up here. So this classifier, it defines the initializer and the forward method. And actually, yeah, let's go through this a little bit slower. We'll go up to the top. All right, so you want to do fine tuning. You want to do model fine tuning. How do we get to that? Firstly, I'm going to get a pre-trained model. This is how I can do that using Hugging Face. Just use the auto model for image classification from pre-trained to get ResNet. So there's my ResNet 50 backbone. I've got that model. Now, if you look in the docs, you can find, in fact, let's look at the docs right now. You'll be able to see in this example, there are a few different things mentioned. There's the model here, which has got from pre-trained like that. And then there's this feature extractor. Now, I mentioned feature extractor earlier. The feature extractor is basically the model without the head. The head's already been taken off. So using this auto feature extractor is a good shortcut to get straight to just the head. And then you add layers layer onto that. But firstly, let's look at just getting the whole model. So I've got the whole model here. If I run this, I'm going to need to run everything above that, aren't I? Yep. Let's just give that a sec to run. No module name transformers. If that ever happens, all you got to do is pip install transformers.
It's just
So that's done. We've got transformers. Now run this cell. Just found this snippet on Hugging Face. Again, like I don't remember this class. I don't remember what I need to import. Just look it up. Get the model, downloading the model. This one, it's not that big. It's pretty big though. Downloads the binary file from PyTorch. So we got the model now. Now, if I print the model, it prints this. Oh, it actually prints exactly the same thing. There's a lot in there. Wow, look at that. So I printed the model. It showed me all of this. It says ResNet image classification, and it shows me all of the different PyTorch modules which exist inside. Those include, you can see it's got this embedder. It's got this thing called an encoder. Wow, it's very deep. It's 50 layers deep, extremely big model. And all through that, you can see exactly what's happening at each step, right? So in here, there's a torch.sequential. It applies a convolution, normalization, activation, so many times, okay? This is a really big model. It's 50 layers deep. And at the end, then you can see this classifier. This classifier, this is the head. So this is the final layer of this ResNet model, which flattens out the outputs from the layer before, which, because it's a computer vision model, it's actually 2D, not vector. We haven't covered that, so don't worry too much about it. And then it adds this linear layer. This linear layer is the one which takes in the 2048 different high-level features extracted by the main body of the ResNet 50, and then it combines them into 1,000 different nodes here, which are the logits for the classification probability of each of the 1,000 classes in ImageNet. So this is basically the classification layer. And this head, this whole thing, this is the thing we want to remove. Because these parameters in here, they've already been trained to combine the high-level features into classifications. So if you pass through some examples which are of a particular type, then it's gonna give you essentially the probabilities of those classes rather than all of the rich feature information in the layer before. Question?
These two lines are the link between the penultimate layer and the output.
Exactly, yeah. The output of this classifier, that is the output, basically, yeah. So what comes out this linear layer is the logits, which are the unnormalized probability distribution. Nice. Sweet. Simple, right? We're all here still so far. Pretty deep in, but it seems like I'm making good progress. So the question is, once you've got that model, how do we replace the head? Well, the way that this works, firstly, actually, let me just go up here. I printed the model, but these things are actually all available in the .modules, like that. So if I run model.modules, it will print all of the different modules, that is the building blocks of transformation, which exist inside this network. And you can print other useful things about the model as well. If you don't know what it contains, you can print dir of model. It'll show you all of its methods and attributes. So you can see all the different things it can do. It can call, it can do other stuff. It's got attributes.
Own magic methods,
not necessarily magic methods, but also including magic methods. All methods and attributes come out of this function. So you can see in here, you can see there's a lot of stuff in ResNet, of course, but you know, there's like load pre-trained model. Somewhere in there, there'll be the classifier. It has an attribute called the classifier. And we can replace that as you can do in this line here. So the classifier is just a torch layer. So I can set it equal to torch.nm.sequential. I got to include the flatten again because it's just a vision model. And then I can add my own head to it. So this is where I add a linear head to combine the 2048 high-level features into 3 final logits for my particular problem. And that's me replacing the head.
So here, how would you make like a 2-layer?
If you wanted to make a 2-layer head, let me expand this out, and then it should become somewhat clear. So who can help me here? How would I make a 2-layer head? Maybe you can help yourself.
I guess you just more than the
That's pretty good. I'm missing one thing though. What am I missing? Got the flatten. I'm missing the activation function. Thank you down there. Yep, so something like that. That's a 2-layer neural network head that you've added onto the end of the model there.
And how would you place the final 2 layers instead of just the classifier?
Yeah, how would you replace the final 2 layers rather than just the classifier? That would be harder. You could do it through iterating through the layers, but it might get a bit messy. Generally, most models have a kind of a conventionally designed. Most models have a conventionally designed feature extractor, which is basically everything up until a certain point.
And you can always retrain.
Yeah. You can retrain everything as we'll look at in a second. So I'm going to remove those for now. So we'll just have a single linear head on the end of that. But that's good. So we've replaced the head there. Now, a lot of Hugging Face models especially have this alternative approach, which is to use the auto feature extractor. So a lot of models have a feature extractor attribute, or how does it work actually? Well, you can basically get the feature extractor from this, which is the whole model up until a certain point. So if you call this model on data, you'll get out not the predictions, but you'll get out the high-level features at the end. And so this stuff you can just stack ahead directly on top of. And so the way you might do that, this one actually looks a little bit longer now that I write it out. But I've defined a new model called the classifier, and I've initialized it with an attribute called the feature extractor, which is that. And then I've defined the head. And in my forward method, I've taken the input data, pass it through the feature extractor, and then pass it through the head. So you can just compose these all together. So just like each different transformation you can apply, like torch to end.linear, is a building block, the auto feature, well, the feature extractor is also just a building block which you can apply in your forward method. So you can compose all of these things together and build on top of what other people have spent a long time building on. So that's my new model there. 2 ways to do that: either replace the head directly. I actually quite like that way here because it's just a one line. Well, it was. And now, or alternatively, you can put it into a whole model like that. So the only thing we're missing is the training. It's the final training down here. And so the 2 methods I mentioned, either weight freezing, that's where we freeze all parameters of the backbone and only train the head from scratch. Or alternatively, we'd use discriminated learning rates, which is where we have 2 optimizers. One with a low learning rate, takes small updates for the backbone, keep it mostly as it is, and another which can make fast updates to the head. Firstly, let's look at the weight freezing classifier. I would have loved to code this up as we go, but I think it's run out of time, so we'll just go with this. So here, I've composed another model on top of this one. So this is my weight freezing classifier. It inherits all of the methods, including the forward, the initializer, from my classifier. So it's basically, imagine I define my classifier, but with also these extra methods. Now it's got 2 methods: freeze weights and unfreeze weights. So in the freeze weights, I just use the dot parameters method that we saw previously, the same thing we used to get the parameters to give to the optimizer. And I can just iterate through each of those parameters and then set their requires grad equal to false. And then do the same in unfreeze weights. So to train with weight freezing, here's my training function. It looks slightly different. And, well, this is actually the only difference. It's just freeze the weights before. You get the model, you freeze the weights, train it as is. You take this optimizer, and this model.parameters now is only going to return, it's going to pass all of the parameters to the optimizer, but the only ones that are going to have their .grad attribute populated are those with requires grad equal true. So actually this is fine, you know. And then the same thing, you know, make the prediction, calculate the loss, set the grad, update the parameters, zero the gradients. That's an example of the training loop with weight freezing. So how would I do it with discriminated learning rates? I've described the process. You've got two different optimizers. They optimize different weights with different learning rates. Can anybody kind of describe to me how I would do that before I show the answer below?
Which ones? Can you say again?
Yeah, so what I'm going to do is I'm going to take a pre-trained model with a new head on, or with replaced head, and those two different parts, I'm going to have two different optimizers. I'm going to have a slow optimizer for the backbone because I want it to stay mostly as it is, and I'm going to have a fast optimizer for the head because that one is totally random, so it should just be able to update as fast as it needs.
So you need to do some conditional statement as you go through it, such that, and you need to define two different optimizers.
Define two different optimizers. Yeah. What do I pass to each of them?
So the one that is for the main bulk of your model,
The backbone.
yes, you will pass the weight freezing.
Pass the weight freezing.
You will that will be the slower one.
But what will I actually pass to it? Anybody help?
For the slow one, you pass all the model parameters, and for the fast one, just the last weights.
Yeah, you don't want to pass all of them to the first one though.
Or back from the last.
Yeah, you want to put. So, but how would I write that in code? So I've got my
So
model.
you have to set false for some and true for some, and then switch it.
Uh,
It requires grad.
So they're all going to have requires grad equal true. In the case of discriminated learning rates, all the gradients for all the parameters will have requires grad equals true. Suggestion?
Can you just do like where it says optimize equals and then instead of model dot parameters, can you just do feature extractor parameters for the slow one? And then I'm not sure about the head, I think you have to define this separately. One of them.
Yeah, so let's look at where's the model? So here's the model, right?
Yeah.
These two things, they are both modules. They're both torch building blocks, which means they have the method parameters individually. So you're right, I think you're on the right lines. I can call my classifier dot feature extractor dot parameters to get all the parameters just for the feature extractor. And I can call my model dot head dot parameters to get all the parameters for the head. I can initialize two different optimizers with a different learning rate. And then how do I make the update steps then? In the bottom of the loop. Exactly. Yeah. Two different optimizers. They're both going to step. They're both going to zero grad. So overall, it looks like doesn't look like that. It looks like this. So here's the backbone optimizer. It takes in those are not correct. It takes in model.featureExtractor dot parameters, and then the head optimizer takes in model.head.parameters.
And
So-
we wrote that feature extractor because we wanted to get those features as we went. Like we wanted the feature extractor because we wanted to get those parameters from the back.
Yeah, exactly. So we don't want these to change too much. So we set the learning rate to low because we hope that these parameters in the feature extractor, they're probably pretty good already. You know, ResNet knows a lot about images. It has done the hard work of combining raw pixels into useful things. So we don't want to change that one too much. Question from the back?
Yeah, correct me if I'm wrong. Doesn't your feature extractor still include classifier then?
Doesn't it include my what, sorry?
The feature extractor still includes the classifier.
You're pointing somewhere. Where are you pointing?
The model dot feature extractor
Yeah.
that we created, that still contains the classifier layer.
This one doesn't contain the classifier because where it came from was the auto feature extractor. And the auto feature extractor only gets the layers up until the head. And so that's the difference in the documentation here between the feature extractor and the model. Cool. Great question. Great question. Nice. So guys, I'm gonna leave you to run through that stuff. Hopefully that was helpful. Another question. Hang on.
Maybe in a million possible, but I'm relearning it with the models with the picture perspective. But like you said at the beginning, I use it quite nice with just the model of the classifier. Wondering not the picture, just the line, the classifier, and the take in one line with case without actually see where it's from.
Let's go over this in a second because I think it needs a bit more detail. Let me wrap up now, guys. So yeah, I'll leave you to go over that stuff. I think this stuff, it can be really good starting point for you to use this in your own projects. Please let me know if there's any questions or issues you have with it. Tomorrow, we're launching Deep Learning for NLP. So be there for the next few lessons to cover how all this stuff applies to language. And tomorrow, we're going to be in a different lecture theatre. That's an important note. We're going to be in the Saïd Business School Nelson Mandela Lecture Theatre, same time as usual, for tomorrow and Wednesday. So don't catch us here. Tomorrow, there's going to be a cash giveaway. And at some point this week, if it gets there in time, there'll be a merch giveaway as well. You know what you have to do. Just post about how epic this is online. Tag me, tag AiCore. Talk about building the future, and I'll see you tomorrow for the giveaway.